Welcome to The Explainer. Today, we're diving straight into a piece of tech that is literally reshaping how we interact with information, computers, and honestly, even each other. Yeah, I'm talking about large language models, or LLMs. Think about it. If you used a chatbot to sum up a meeting this morning, or had your email autocomplete a sentence, or maybe even asked a machine to write some code for you, you've already used this exact technology. They are absolutely everywhere right now, and their transformative nature is something we all really need to understand.
But before we get into the nuts and bolts of how they're used today, we kind of have to step back and ask a really fascinating question. How did machines actually learn to speak? Just think about this for a second. We've had modern computers for nearly 80 years, right? But machines only truly learned to converse fluently in the last handful. It's a wild journey that takes us all the way from basic statistical math and simple neural networks, straight through to the incredibly fluent, context-aware text generation that we see today. The leap from simple math to fluent conversation, it's easily one of the most exciting stories in modern science.
So, we're going to decode LLMs from the ground up. We'll start with their historical roots, zoom right into the actual architecture that makes them tick, try to wrap our heads around the massive scale of data they require, look at their real-world applications across various industries, and finally, take a really objective look at the profound challenges they present. By the end of this, you are going to walk away with a crystal-clear understanding of the engine that's driving modern AI.
Here's our roadmap for today. First, the rise of language models. Second, inside the transformer architecture. Third, scaling up, data and parameters. Fourth, real-world applications. And fifth, challenges and the future. Let's get right into it.
Okay, let's dive into Section 1, the rise of language models.
You know, the timeline of machines learning language is actually way longer than most people realize. Way back in the 1940s, Warren McCulloch and Walter Pitts first introduced the world to the whole idea of artificial neural networks. Now, for decades, progress was pretty slow, mostly relying on super strict rule-based coding. Then in the 80s and 90s, we saw the introduction of statistics-based language models. Basically, they were using probability to just guess the next word. Fast forward to 2010, and neural networks made a huge comeback with the RNLM. That's the Recurrent Neural Network Language Model. If you remember that era where your phone's autocorrect suddenly started getting just a little bit better at guessing your next word, yeah, that was RNLM starting to capture those sequential dependencies in text. But the absolute turning point, the real game changer that completely flipped natural language processing on its head, happened in 2017 with the introduction of the transformer model. And that eventually paved the way for the massive models we see today, like the release of GPT-4 in 2023.
Which brings us to Section 2, inside the transformer architecture.
So, what exactly happened in 2017? Well, we got the transformer architecture. I know this looks a bit complex, but stick with me, we'll break it down together. Unlike older models that process text just one word at a time in this slow, linear sequence, the transformer uses something called a self-attention mechanism. To put it simply, instead of sounding out a sentence word by word like a toddler learning to read, the transformer looks at the entire sentence all at once. This lets the model figure out global input-output dependencies instantly. It massively reduces training time while understanding context on a completely different level.
All right, let's walk through this pipeline step by step. First up, we have input embeddings. Since machines really only understand numbers, this step translates human words into a mathematical space. But it's not just a simple dictionary, it actually maps out concepts. In this math space, the numbers for king and queen are grouped closely together, while a word like apple is, millions of miles away. It's how the machine grasps meaning without actually knowing the words. Second is positional encoding. Because neural networks don't naturally get word order, this step tags each word with a little mathematical stamp showing exactly where it belongs in the sentence. Third is the encoder. This processes all that data to uncover hidden, abstract patterns in the text. And finally, the decoder takes all that rich context and learns to predict the very next word in a sequence. It really is a brilliantly elegant flow of data.
Moving on to Section 3, scaling up, data and parameters.
Now, what's really interesting here is that the transformer architecture alone just isn't enough to achieve the crazy fluency we see today. You have to scale it up massively. We measure these models in parameters, which you can kind of think of as the neural connections or the brain power of the model. Back in 2018, GPT-1 had 125 million parameters. A model like BERT Base had 340 million. But then, look at the massive leap to GPT-3 with 175 billion parameters, and finally, GPT-4 with a staggering 1.8 trillion parameters. No way, right? To put 1.8 trillion into perspective, if each parameter was a single grain of sand, you'd have enough sand to completely fill several Olympic-sized swimming pools. It is exactly this unprecedented scale that lets these models comprehend highly intricate linguistic patterns and generate text that feels undeniably human.
But to train a brain with 1.8 trillion connections, you need an unimaginable diet of data. I mean, these models consume massive datasets to learn about the world. They're reading vast swaths of the internet, like open web text and Wikipedia. They literally digest entire libraries of books and news articles. They process highly dense scientific data from sources like PubMed, and they even learn logic by reading raw code from repositories like GitHub. And what's really fascinating is how specialized this diet can be. A model like Llama consumes a highly diverse diet across all these categories to become a really good generalist. On the flip side, a model like AlphaCode focuses entirely on code data, making it a highly specialized programmer.
Let's look at Section 4, Real-World Applications.
So we've seen the history, the architecture, and the sheer scale of it all. Now, how does this actually impact global industries? Well, the impact is incredibly diverse. In healthcare, specialized models like BioGPT are trained on biomedical literature to analyze complex clinical text. We're even seeing models being evaluated as decision support tools for breast tumor boards, and they are aligning highly with human clinical recommendations, which is huge. Now, contrast that with agriculture, where variations of transformer models are analyzing massive hubs of soil data, weather data, and satellite imagery. They're out there helping farmers optimize irrigation, predict crop prices, and even anticipate natural disasters. It's kind of wild to think about, isn't it? The exact same fundamental mathematical architecture solving crop yields is the exact same math recommending your next movie or helping doctors review medical charts.
And of course, we can't forget social media. LLMs are completely revolutionizing social platforms behind the scenes. They're aiding in content production, basically acting as sophisticated writing assistants. But more importantly, they are performing automated sentiment analysis at absolute scale to gauge public opinion. They use something called named entity recognition to categorize vast amounts of text, and they act as an absolutely crucial line of defense by rapidly filtering out dangerous or improper content to moderate these platforms.
Which brings us to our final section, challenges and the future. Now, as amazing as all this is, this technology definitely is not without its significant hurdles, and we really need to objectively look at the current scientific consensus regarding these limitations. The scientific literature points out several critical, well-documented challenges. First up, there are documented inaccuracies and hallucinations in the text they generate. This is often due to a lack of real-time updates in their training data, so they can generate answers that sound highly plausible but are actually completely incorrect. Furthermore, the sheer energy consumption and the environmental impact of training these massive models is becoming a major growing concern. But perhaps the most fundamental issue is transparency. There's a profound lack of interpretability here. Because of those trillions of parameters we talked about, the model functions largely as a black box. We can see the inputs going in and the outputs coming out, but tracking the exact logic path the machine took to get there, that remains a massive, unresolved scientific hurdle.
Large language models are, without a doubt, a monumental leap in artificial intelligence. They're built on decades of research, that elegant transformer architecture, and an unbelievable scale of data. But it leaves us with a really profound question to ponder. As these models grow larger, billions of times more complex, and more integrated into our daily lives, who is really doing the reasoning? Is it the machine developing its own logic, or is it simply a flawless mathematical mirror reflecting the massive ocean of human data we fed it? Well, until we know the answer, the mirror keeps reflecting. Thanks so much for joining this explainer.